All right, today we are going to be learning how to simplify radicals as well as perform operations with radicals. So we're going to start with just the simplifying, and don't worry, we're not doing all of these problems, nor do you have to do all of these problems. You have a very short assignment, and it is not the entirety of this paper. So if you were worried about that, you don't need to be. We're not doing all of this right now. So when we are simplifying radicals, the big rule is that you cannot have any perfect square factors under the radical. So this is the big idea, and this is the first rule that we have to follow. Now, in order to know if we're in violation of this rule, you really have to know what your perfect squares are. So I always like to start this type of lesson out by making a list at the very top of our page of the perfect squares. So if I do 1 squared, that's 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. You see where I'm going here, right? 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. 9 squared is 81. 10 squared is 100. 11 squared is 121. 12 squared is 144. If you know all of those perfect squares for right now, you should be in pretty good shape for all of this. So when we say we can't have any perfect square factors, that means that the number underneath, which we call the radicand, cannot be divisible by any of these numbers other than 1, because obviously everything is divisible by 1. So we don't really need to worry about the 1. You can cross it off, but we can't have any numbers that are divisible evenly by any of these in the list. So when I look at the first problem here, radical 8, the reason why this is not in simplest form is because 8 is divisible by the perfect square 4. Specifically, if I were to rewrite 8 as a product of factors, 8 is 4 times 2. And so I'm going to teach you 2 different ways to simplify radicals, and one of them, which is called the biggest perfect square method, starts off like this. You look at your list and you decide, okay, what's the biggest number in this list that 8 is divisible by? Well, that one's an easy one because 8's smaller than everything but 4, so you know it can't be divisible by anything bigger than it. So once I realize it's 4 times 2, then I basically just give them each their own symbol. And when I do that, hopefully it pops out at you that, oh, the square root of 4 is 2, because most of you know that. So that gives me 2 when I simplify the square root of 4. The square root of 2 does not simplify because 2 is a prime number. And so that becomes my final answer. And we read this 2 radical 2. So if I were going to do another similar to this, if I look at this one, for instance, 18, when I look at my list, 16, 9, and 4 are the only numbers smaller than it. It's not evenly divisible by 16. It is evenly divisible by 9. 18 is 9 times 2. So then this looks very similar to what we did over here. I give them each their own symbol, square root of 9 times square root of 2, and then the square root of 9 we know to be 3. And so 3 radical 2 becomes my answer. So what I would like for you to do now, for the first one to practice on your own, using this same method, is to do number 2 here with the 12. So you look at 12, it fits in here. So you ask yourself, is it divisible, evenly divisible by 9? If it is, write it out like this. If it's not, then try 4. Write it out, give them their own symbol, and then simplify. And then once you've got your answer, go ahead and select it. So let's go ahead and check your work. Hopefully you realized, since 12 is in here and it's not evenly divisible by 9, that 4 is the number we're looking for. So 4 times 3 is how we get 12. So then give them each their own symbol. Square root of 4 times the square root of 3. And the square root of 4 is 2, so just like over here, except this time what's left inside the radical is a 3 instead of a 2. So this is 2 radical 3 for your final answer there. Okay, so that's the biggest perfect square method. Then I'm also going to show you what I call the factor tree method. So you guys, I know, have done factor trees because I've seen my kids do it and they're younger than you. So I'm quite sure you know what I'm talking about when I say a factor tree. So I'm going to show you on number 5 here, one factor tree, then we'll do another before I have you try it yourself. So on 27, it doesn't matter what factors you break it down into. So I'm going to say 27 is 9 times 3. And then you keep continuing the branches until you have prime numbers. 3 is prime, but 9 is not. 9 breaks down into 3 times 3. So we've done the factor tree. The way we use the factor tree method is something I like to call the matching outfit party. So it's like right now, all of these factors are stuck inside the house that is the radical. And they really want to go outside the house to a party. But this is a matching outfit party, and you have to have a friend or special someone to wear a matching outfit with in order to go to the party. So because these are the same number, they have matching outfits. So these two threes can go to the party together. But this matching outfit party is only for couples, no trios, no singles. So this 3 does not have anyone to wear its matching outfit with because these two are already coupled up. So that means this 3 is not allowed to go to the party. It has to stay inside the house. When these 3s that are matching outfits go to the party, they are one couple. So that means that instead of writing 2 3s on the outside, I just write 1 because in their matching outfits, we can't tell them apart. And this becomes my answer, 3 radical 3. Now, I know that's a lot of stories and seems maybe a little bit confusing, so I'm going to do a couple more before I have you try it. So 48 can break down into a lot of factors. It can be 16 times 3. It can be 4 times 12, which is what I'm going to do because I think that's the one that most people think of. 4 is not prime. It breaks down into 2 times 2. 2 is prime, so that branch is done. 12 breaks down into 4 times 3. 3 is prime, but 4 is not. And now everything on the end of a branch is prime. So when I go to figure out the matching outfit party, these 2 2s can wear a matching outfit. And these 2 2s can wear a matching outfit. And this sad little 3 is stuck in the house. So 3 is inside the house still. These both become a single 2 because we can't tell them apart. So this gives me 1 2. This couple of matching outfits gives me another 2 on the outside. Anything that we have on the outside, we then multiply. 2 times 2 gives me 4. So the final answer here would be 4 radical 3. All right, last one I'm going to do here. Number 9, 72 One set of factors for 72 is 9 times 8. Neither is prime. 9 breaks down into 3 times 3. 8 breaks down into 4 times 2. 4, 2, and 2. Now we're all prime. So we've got a matching outfit here. We've got a matching outfit here. I know now from the example that I did in 7 that when I have two things on the outside, I multiply them. So a single 3 times a single 2, because I've got 3 times 2 on the outside, gives me 6. And then the only thing stuck inside this time is this 2 that didn't have a matching outfit. So 6 radical 2 is our final answer there. All right. I would like for you to do number 10, radical 80. So make yourself a factor tree, find the matching outfits, and then select the correct final answer. All right, so let's check your work. 80, most people, the first set of factors they think of is 8 times 10. But again, on any of these, it doesn't matter which factors you pick first. You're going to get the same numbers at the end of your branches. So that part doesn't matter. 8 is 4 times 2. The 2 is prime, so it's okay. This 4 is not, so make it 2 times 2. 10 is not prime either. It breaks down into 2 times 5. Both of which are prime. So be careful because I didn't go straight down here. So don't think that 4 is at the end of the branch. So I got a pair of 2s that can go to the matching outfit party. And then I have another pair of 2s in here. So 2 times 2 on the outside. The only thing left at the end of a branch that doesn't have a matching outfit is the 5. So 2 times 2 is 4. And so my final answer when I simplify radical 80 is 4 radical 5. Just to be clear, in case you haven't tried it already, this is not something that your calculator does for you. So you can't just type in radical 80 and expect to get this answer. It's going to give you the decimal equivalent, which is not worth any type of points when we're trying to simplify. This we're going to use a lot in the things that we do here coming up in second semester. So that's why we're learning this skill and previewing it, because you're going to need to have this skill for what we learn later. 11, I just want to point out, sometimes they try to trick you. 100 is a perfect square. Don't do a factor tree and waste your time. The square root of 100 is 10, and that's the answer. Okay. Now, in the rest of the examples we're going to be doing, we're going to be dealing with operations for radicals. So first, we're going to look at when we square a radical. And the rule for squaring a radical is that it gives you that same thing, but without the radical symbol. So radical 5 squared should be the same number, 5, but with no radical symbol, so meaning just a plain 5. Now, you don't need to show me any work for this problem because this is the rule, but I do want to show you why it's the rule, because if I do radical 5 times radical 5, radical times radical stays under the radical, square root of 25 is 5. So that is why. If I have something like what I see here in number 3, this whole thing is squared, and so it's telling me to multiply it by itself. So this means 2 radical 3 times 2 radical 3. The rules for multiplying with radicals is that we multiply plain numbers times other plain numbers and radicals times other radicals. So I do the 2 times the 2 to get 4. Any radical times itself, we said, is the same thing, but without the radical symbol. So radical 3 times radical 3 gives me plain 3, and then 4 times 3 gives me a final answer of 12. So let me show you one more time, and then I'm going to have you try one. So here, 10 radical 7 squared. It's 10 radical 7 times 10 radical 7. So I do 10 times 10, which is 100. Radical 7 times radical 7 is plain 7, and 100 times 7 is 700. So now I would like you to do number 6, 8 radical 2 squared. So go ahead, write down your work, and then choose your correct answer. All right, so checking your work here, 8 radical 2 times 8 radical 2. 8 times 8 is 64. Radical 2 times radical 2 is plane 2. And 64 times 2 is 128. So final answer there. Part 3, same idea. We are still multiplying, except we're not multiplying it by itself anymore. So here in number 1, when I look at that one, there is no plain number on the second one. So that's as if it were a 1. So I do 2 times 1 to get 2. Radical 5 times radical 5 to get plain 5. And 2 times 5 gives me 10. Here in number 4, I do 4 times 3 to get 12. I do radical 6 times radical 3 to get radical 18. Now this one is a little bit different because radical 18 is not in simplest form. So that means we now have to kind of check our work and say, okay, well, radical 18, I already once on this paper did that problem. Radical 18 is really 3 radical 2. So that means that this is 12 times 3 radical 2. 12 times 3 is 36. So 36 radical 2 would be what we would end up with here. In a problem like number 2, I do the 3 times the 5, which is 15. I do radical 3 times radical 2, which is radical 6. But this time 6, even though it's not a perfect square, 6 breaks down into 3 times 2, but there's nobody to go to any matching outfit parties. And if we're looking at the biggest perfect square method, you can see 6 isn't divisible by any of these perfect squares. And so there's nothing else I can do to that, and that would be my final answer. So that's what we do when we multiply. The very last thing we're going to be doing in today's lesson is learning how to deal with adding or subtracting radicals. Now, the biggest rule here is that they have to be in simplest form first. And the questions you're going to be asked, many of them will already be in simplest form. But if we can do the hard ones, then hopefully you'll be fine with the ones that are easier in your practice problems. So I'm going to pick number 1 because I've already simplified both of those radicals earlier. Radical 18, we just said, is 3 radical 2. Radical 8, we did in the first problem up here, it's 2 radical 2. So when we multiply radicals, we do plain numbers times plain numbers and radicals times other radicals. It does not work that way for adding and subtracting. In order to add or subtract, you have to treat the radicals like variables. And what I mean by that is if you have 3x plus 2y, there's nothing you can do with that. It stays 3x plus 2y because they're not like terms. Here, it's the same idea. The only way that you can simplify is if the radicals have the same radicand, meaning the number underneath the radical. So when you first would look at them, you would say, oh, nothing I can do, they're not the same. But that's because they weren't in simplest form. Now that they're in simplest form here, this is the same thing, or same idea. It's not the exact same thing, but it's the same idea as saying 2x plus 3x. And hopefully all of you would tell me 2x plus 3x is 5x. So it's the same thing here. If I have 2 radical 2's and I add 3 more, I have a total of 5 radical 2's. Same idea for subtraction. When I look at number 4, The square root of 500, I haven't broken that one down yet. I'm going to use the biggest perfect square factor because I can very easily see that 500 is divisible by 100, and this is a faster method than factor trees. Square root of 100 is 10, so that's 10 radical 5. 20 is 4 times 5, which square root of 4 is 2. So I have 10 radical 5 minus 2 radical 5. If I have 10 of something and I take away 2, I end up with 8. So 8 radical 5. All right, very last example here we're going to do is number 5. I'm going to break it down for you, and then you're going to come up with the final step for the last answer. So 99, biggest perfect square it's divisible by is 9. It's 9 times 11. Square root of 9 is 3. So simplest form is 3 radical 11. So then radical 44, that's 4 times 11. And the square root of 4 is 2. So I have 3 radical 11 minus 2 radical 11. And I want you to go ahead and tell me what that final answer would be. All right, so I had 3 of something. I took away 2 of them, which means that I have 1 left. Now, just like we wouldn't write 1x as a final answer, we would just write x. Same idea here. 1 radical 11 is really just radical 11, and this is my final answer. So hopefully that makes sense. Please make sure you reach out if you have questions on the examples.